Two small identical circular loops marked 1 and 2 carrying equal currents are placed with the geometrical axis perpendicular to each other as in figure. Find the magnitude and direction of the net magnetic field produced at the point O. So we are asked to find total magnetic field in magnitude and the direction of total magnetic field due to coil or loop 1 and 2 at point O. And from question, okay, we have identical loops 1 and 2. And for identical loops, okay, radius is same or is equal. So we have this. Therefore, let R be the radius of loop 1 and 2. And we find, okay, loop 1 is carrying current I, and the direction of current is given in the question. And loop 2 is carrying equal amount of current, that is I, okay, and the direction of current is shown in figure. And point O is at X distance from the center of the loop 1, and point O is at distance X from the center of the loop 2. So we have this, okay. Now, at first, okay, what we do, we find the magnitude of magnetic field produced due to loop 1 and loop 2 at point O. Now, in order to find the magnitude of magnetic field, okay, at point O, we use the concept, okay. So I'm writing for finding the magnitude of magnetic field at point O, we use the concept of magnetic field at a point. So I'm writing in this way, okay. Field at a point on the axis of current carrying circular coil. So we use this concept, okay. We use the concept of magnetic field at a point on the axis of current carrying circular coil. So we have this, okay. Let's say we have circular coil, okay, with R as the radius, and let I be the current flowing in this circular coil, and current can flow in clockwise or it can flow in anti-clockwise direction. And this is the center. So this is the axis. So this is the observation point, okay. This is the observation point. where we are interested to find the magnetic field. And let this point be at distance x from the center of the circular coil. So magnetic field at this point, okay, magnetic field at this point is given by B equals mu naught n, where n represent number of turn or turns, I current flowing in the circular coil, and square of the radius of the circular coil divided by 2 bracket r is square plus x is square whole power 3 by 2. So we use this expression, okay, or we use this concept in order to find the magnitude of magnetic field due to loop 1 and 2 at point O. Now, so at first we find or determine the magnitude of magnetic field. Now, at second, or then we can write in this way. What we do, we use right hand thumb rule to determine the direction of magnetic field at point O due to loop 1 and 2. So we have this. Now, let us first, okay, let us first determine the direction of magnetic field. So we can see from the question, okay, loop 1 is in vertical plane. So I'm drawing in this way, okay. Loop 1 is in vertical plane and loop 2 is in horizontal plane. So I'm drawing, okay, and this way. So we have this. So this is loop 1 and we have identical loop 2, okay. And we can see in loop 1, current is flowing in clockwise direction. So if we rotate or crawl the finger of right hand in the direction of current, then the thumb gives the direction of magnetic field. So magnetic field at point O, due to loop 1 is directed towards loop 1. So we have this. Clear? So we have this. Now, let's come to this figure, okay? So we can see the coils are placed in such a way that, okay, the geometrical axis perpendicular to each other. So this is the geometrical axis. This is the geometrical axis, okay? And this is the geometrical axis. So we have this. So this is the geometrical axis of loop 1 and this is the geometrical axis of loop 2. And they are perpendicular to each other, okay? So we have this. Clear? And the distance, this distance, okay, is x, and this distance is again x. So we have this. And as I said earlier, current in loop 1 is flowing in clockwise direction. So when we crawl the finger of right hand along the direction of current, okay, then the stress thumb gives the direction of magnetic field, okay, and the direction of magnetic field due to loop 1 at point O is directed towards loop 1. Now, again in loop 2, okay, we find current flowing in anti-clock direction. So we find current flowing in anti-clock direction. So when we crawl or rotate the finger of right hand in anti-clock direction, that is along the direction of current, then the stress thumb gives the direction of magnetic field. So magnetic field at point O, okay, due to loop 2 is directed along this direction. So we have this. Okay? We have this. So we have B1 acting towards loop 1 and B2 acting away. Okay, it is directed away from loop 2. So in this way, using right hand thumb rule, we have determined the direction of magnetic field at point O due to loop 1 and loop 2. Now, let us find the magnitude of magnetic field, that is B1 and B2. Clear? So I'm redrawing the figure, okay? So we have this. This is loop 1. Current is I, and the radius is X. Sorry, radius is R, okay? And this distance is X. This is point O. So the magnitude of magnetic field, okay? B1. So what is this? This is magnitude of magnetic field at point O due to loop 1. So B1 equals, as I said earlier, we use this, okay, relation mu naught n I r square by 2 r square plus x square whole power 3 by 2. So this is the magnetic field at a point on the axis of current carrying circular coil. So you can see, okay, we are using this equation. Now, since the number of turn n equals 1, so we can write B1 equals mu naught, n is 1, okay, I r square by 2 bracket r square plus x square, okay. Point O is at x distance from the center of the loop 1, okay, and whole power 3 by 2. So we can write mu naught I r square divided by 2 r square plus x square whole power 3 by 2. So we have this. Okay. Or let me write in this way, okay. Therefore, B1 equals mu naught I r square by 2 r square plus x square whole power 3 by 2. This is equation 1. So we have this. Now next, okay, we have loop 2, okay. We have loop 2 carrying current I, and this distance is x. Now And the radius of loop 2 is R, and number of turns is 1. So loop 2 is having single turn, okay? So I'm writing over here. This is magnitude of magnetic field at point O due to loop 2. So we have this. Therefore, B2 equals mu naught number of turns. We use this equation, okay? Number of turn is 1 I R square by 2 R square plus X square whole power 3 by 2. Therefore, we can write B2 equals mu naught I R square by 2 R square plus X square whole power 3 by 2. This is equation 2. So we have this, okay? And we know, okay, B1 is directed towards loop 1 and B2 is directed along this direction. It is directed away in upward direction, okay? This is B2 and this is point O. Now, we must find the resultant, okay? So I'm erasing this. We must find the resultant of B1 and B2, clear? So I'm writing, let B T, okay? So I'm writing in vector form. So this is resultant of B1 and B2. Or we can simply tell, okay, or we can simply write in this way. This is net or total, okay, magnetic field, okay? This is in magnitude. Magnetic field at point O due to loop 1 and 2. And we can see, okay, what we can see comparing 1 and 2, okay, we find magnitude of B1, okay, equals magnitude of B2. Therefore, the resultant, okay, the resultant BT, okay, that is total magnetic field divides the angle between B1 and B2 into two equal parts. So we have this. We can see this whole angle, okay? So I'm drawing over here. This is B1, this is O. This angle is 90, this is B2. So we have this. So what we find? We find this, okay? Resultant magnetic field, okay? It divides. So let me redraw, okay? This is B1. This is B2, okay? This is point O. So the resultant divides angle into equal parts. And what we find, this total angle, okay? This is theta equals 90 degree. So it is dividing 90 into two equal parts. So we have this. Okay. Therefore, we can write magnitude of resultant or net magnetic field BT equals, using the concept of parallelogram law of vector addition, okay? We have B1 square plus B2 square plus 2B1 B2 cos 90 degree, because angle between B1 and B2 is 90 degree. And since cos 90 degree is 0, so therefore we can write BT equals B1 square plus B2 square, and we know B1 equals B2 in magnitude. Therefore, we can write under root twice B1 square. Okay? So, therefore, BT equals under root 2 B1. Okay? So, we have this. So, we have this. Now, we have BT equals under root 2 B1. And what is B1? B1 is mu naught I R square by 2 R square plus X square whole power 3 by 2. So we have this, okay? You can see B1 is mu naught I R square 2 by 2 R is bracket R square plus X square whole power 3 by 2. So BT equals under root 2, and B1 is mu naught I R square by 2 bracket R square plus X square whole power 3 by 2. So let me write in this view, okay? So this is the total magnetic field. Let us call it equation 1. This is the total magnetic field, okay? So this is net magnetic field, okay? This is in magnitude. This is in magnitude at point O due to loop 1 and 2. So we have this. Now, let us assume this, okay? If, since we have this, okay? This is loop 1. This is X. If X is very, very greater than R, let us use this condition, okay? Then R square plus X square is approximately or nearly equal to, okay, X square. So we can write in this way. Therefore, from equation third, okay, total magnetic field BT equals under root 2 mu naught I R square by 2, and we have x square whole power 3 by 2. So we are using this, okay? We are using this, and this cancels out. So we can write BT equals under root 2 mu naught I R square by 2 x power 3. So this is the total or net magnetic field at point O when x is very, very greater than r, that is the radius of the circular loop. Now, in order to find the direction, okay, let us find the direction. Let us discuss direction of net magnetic field at point O. And we know B1 acts along this direction and B2 acts along this direction, and the resulting divides angle between B1 and B2 into two equal parts. And we have seen in the previous case, okay, we find BT makes angle 45 degree with B1 and B2. So this angle is 45 degree and this angle is 45 degree. Therefore, we can tell net magnetic field or we can write in this way, okay, makes angle 45 degree with axis of the loop 1 and 2 as in figure, okay. So net magnetic field makes angle 45 degree with the axis of the loop 1 and